How you doing today? I hope you're doing well. Hope you're staying safe. Hope you're using social distancing. And I hope you are washing your hands. Okay, today, ladies and gentlemen, we're going to talk about the ratio tests for absolute convergence. Okay? And there are several things you need to know and understand about the ratio test for absolute convergence. And here we go. The series an, as n goes from 1 to infinity, the series will converge if the limit as n goes to infinity of a subscript n plus 1, okay, that's the next term in the series, divided by a to the n, the actual sequence itself, if that absolute value is less than 1. If this is true, then the series will converge, okay? The series diverges if the limit as n goes to infinity of the absolute value. That's why it's called absolute convergence. We're talking absolute values here. So it's going to diverge if the limit as n goes to infinity of a subscript n plus 1, succeeding term, divided by the actual sequence itself, a to the n. If it's greater than 1, then it diverges. The series will diverge if it's greater than 1. And the ratio test is inconclusive if that same ratio, the absolute value of that ratio, as n gets increasingly large, approaching infinity, if it equals 1, then the test is inconclusive. Okay? What's important to know and understand about the ratio test, very well-liked test. It's a beautiful test. It's a wonderful test. Okay? And the ratio test is a test for convergence of a series that primarily involves factorials and exponentials, primarily. But you don't necessarily have to have factorials or exponentials to use it, but it's primarily used for factorials and exponentials. All right, come on, let's look at some examples. All right, here we go. Determine whether or not these series converge or diverge, and of course we're going to use the ratio test to determine our convergence or divergence, okay? So the first thing we want to do is we have to look at this in terms of, okay, we're looking at the summation from n equals 0 to infinity of the absolute value now of, all right, 2 power n over n factorial. All right, now let's use this right here in terms of the ratio test. Let's see what we get. All right, so using the ratio test, we're looking at the limit as n gets very large of the a subscript n plus 1 term. Okay? So we're looking at 2 to the n plus 1. 2 to the n plus 1. See that? Divided by n plus 1 factorial. Divided by a subscript n. So instead of writing this expression, you know, this, and writing, watch this, if I write underneath it the actual expression 2 to the n over n factorial, that's doing too much right here. So I'm not going to write it like that. I'm going to erase that. And here's how I want you to understand it and write it. Not like that. But go ahead and write the reciprocal of an, of the sequence. So give me times. And go ahead and write the reciprocal of this right here as n factorial over 2 to the n, and I want the absolute value of this using the ratio test. You get that? I multiplied by the reciprocal instead of just dividing a subscript n plus 1 over a to the n. I multiplied by the reciprocal right here. Okay? Good? Okay. All right, so now let's go ahead and algebraically expand everything. Here's how you algebraically expand it. Limit as n approaches infinity. Here we go. 2 to the n plus 1. I'll write that as 2 to the n times 2 to the power of 1, of course, because that's what 2 to the n plus 1 is. And then that's multiplied times n factorial, there. All divided by, all right, now, n plus 1 factorial, that's written as n plus 1 times n factorial times 2 to the n. Now you can begin to cancel some factors in the numerator with the factors in the denominator. Let's do that. So our 2 to the n's go to 1, our n factorials go to 1, and we're left with the limit as n goes to infinity of 2 divided by n plus 1. All right, now we're looking pretty good now. 2 divided by n plus 1, even as n gets increasingly large. So where does this expression go? Well, obviously, our numerator is at 2, but the denominator gets increasingly large. So when you have 2 over a very large number, obviously you are approaching 0. Okay, well, is our limit, is it less than 1, greater than 1, or equal to 1? Obviously, it's less than 1. So this series have what we call, it converges. In fact, it is actually absolute convergence. Why absolute convergence? Because we put it in absolute values. The answer is the criteria is less than 1. Absolute convergence. So for any of these problems, if they converge absolutely if you use the ratio test. There's absolute convergence with that. And after these examples, I'll come back and talk to you and explain the difference between absolute convergence and conditional convergence, and et cetera, et cetera. Okay? So stay tuned. Stay with us. All right, let's go to our next problem. Let's see if we have convergence or divergence here. Okay? So the first thing we have to do is go ahead and add the plus 1 term. We know we're going to use the ratio test because I see exponential powers here all over the place. So let's just go ahead and use the ratio test. All right, so here we go. So I have the summation as n gets equals 0, and then it gets increasingly large. All right, so we're going to have n plus 1 quantity squared, check, times 2 to the n plus 2. Because if I make this right here n plus 1, well, that's going to be n plus 1, which is n plus 2. Okay? All divided by 3 to the n plus 1. All right, good. You got that? Have any questions about what I did or what I just explained? Kind of rewind it and listen to it again. All right? Times. Well, don't multiply it by the actual sequence itself. Multiply it by the reciprocal of the sequence. Because again, whenever you divide by the sequence, Or here, multiplied by the reciprocal, okay? Because multiplication and division are inverse or reciprocal operations, right? All right, so the reciprocal here is going to be 3n over n squared 2 to the n plus 1. And as we did on this side, go ahead and algebraically manipulate it and pull it apart, and let's see what things are going to like kind of cancel out. All right, let's do that. And we can put these in absolute values here. And the reason we drop the absolute values is because all numbers in the range from 0 to infinity, if substituted here, they're positive anyway, nothing negative. So since it's positive, you can just drop the absolute values. All right, let's go. Let's do it. So I have my series n equals 0 going all the way to infinity. And here we go. We're going to have n plus 1 quantity squared times 2n times 2 squared times 3 to the n over 3n times 3 times n squared times 2n times 2. There we go. So it's algebraically expanded. We use all the rules of exponents, the laws and everything. And so now let's begin to see what we can cancel out here and eliminate. Let's see. I see a 2n, 2 to the power of n, pardon me. 2 to the power of n cancels out. I see a 3 to the power of n in my numerator and denominator. That also goes to 1. Let's see. I see a 2 here. And I see 4 right there, so I can get rid of that 2 and make that a 1. Okay. Now let's bring it all together and see what we're working with here. So we have the summation of n equals 0 to infinity of 2n plus 1 quantity squared over 3 n squared. All right, let's look at our limit. So we have the limit as n goes to infinity of 2/3. Now let's write n plus 1 squared over n squared as n plus 1 over n quantity squared. Yep, write it like that. Write n plus 1 quantity squared divided by n squared as n plus 1 divided by n, and that quantity is also squared. Okay? And the 2/3 you can take out, and you can write it as 2/3, right, times the limit as n goes to infinity of n plus 1 over n quantity squared. All right. Well, what's happening right here? Well, we can rewrite that as 2/3 of the limit as n gets increasingly large. Now let's divide that out. That's going to be 1 plus 1 over n quantity squared equals. Well, here we go. As n goes to infinity, where does 1 plus 1 divided by n quantity squared, where does that go? Well, we know that 1 over n, that goes to 0. And so this just goes to 1. And so this limit here is 2/3. Question: is 2/3 less than 1, greater than 1, equal to 1? Well, we do know it's not equal to 1. And we do know that 2/3 is not greater than 1. So 2/3 is less than 1. So absolutely this series also converges because it's less than 1. All right? So this series also converges. We have absolute convergence right here. Absolute convergence. Questions? We good? We good? Oops, I forgot to tell you guys. We copied down the notes before we get started. Hopefully I'm out of the way and you can take time to pause it and write down everything, etc., etc., etc. All right? All right. Next example. Now, ladies and gentlemen, with this example, you really do not have to use the ratio test. Many of these tests are interchangeable, you don't have to use it. But for the last example, I would just remind you to always think about the nth term test for divergence first. The nth term test for divergence. Look at what we have here. We have a series, and in this series, I see an exponential power divided by a factorial. And an exponential power function grows faster at a much faster rate than a factorial function, right? So you can use, in this case, as we discussed in our previous lessons, you can use, right, the exponential or the comparative growth rate right here. The comparative growth rate, right? Which says the limit of the faster over the limit of the smaller growing function is going to take us to infinity, right? So this right here in actuality is infinity. And by the nth term test for divergence, the series diverges because its limit is other than 0. In other words, the limit as n goes to infinity of n to the power of n divided by n factorial is infinity. Any value or any expression for the limit other than 0 lets us know that the series is divergent. So this series diverges because primarily of the comparative growth rate and because of the nth term test for derivatives. Nth term test for divergence. Guess derivatives on my mind. Nth term test for divergence, which states that any value or any expression we get other than 0 implies that the series is divergent. So this series diverged. However, if we want to use the nth term test to prove it, we can. Let's take a look at it. Let's use the nth term test. Let's look at the root test, not the nth term test. We can use the root test to prove it. We've already used the nth term test for divergence. Let's use the ratio test to prove it. I'm saying all type of tests right now. I'm saying ratio test, root test, and the nth term test. All these tests, it all becomes a big jumping. All right, ratio test. Here we go. So we're going to look at the limit as n gets increasingly large. All right, do the plus 1 term. N plus 1 to the n plus 1. All over n plus 1 factorial. Multiplied by the reciprocal of this. N factorial over n to the power of n. All right, let's work on it now. And of course, it is absolute value of this, but it's already all positive, so we're good to go. All right, so we have the limit as n gets increasingly large. All right, here is going to be n plus 1 to the n times n plus 1. That's what this expression represents. It's n plus 1 to the power of n times n plus 1 times n factorial, all divided by, what do we have here? N plus 1 times n factorial. See how I lined that up? See how I just lined that up? Because this right here is n plus 1 times n factorial. That's what this expression is. So n plus 1 times n factorial. Now I lined it up. And now I have an n to the power of n. And let's see what happens here. The n plus 1s, they go to 1. N factorials, they also go to 1. And so we're going to be left with the limit as n goes to infinity of n plus 1 divided by n to the power of n, which equals the limit as n goes to infinity of 1 plus 1 over n to the power of n. All right. Now, as n gets increasingly large, goes to infinity, do you recall what this is? As n gets larger and larger, as n gets larger and larger, what is the quantity of 1 plus 1 over n to the power of n, that quantity to the power of n? What is that? What is it? Can't hear you. Oh, I can't hear you no way. If you said E, you are correct. So this equals E. Now the number E, that irrational number, not terminating, not repeating, that irrational number E, is E bigger than 1, smaller than 1, or equal to 1? What do you say? All right, you got it. E is 2.718281828, on and on and on and on. This is larger than 1. Which means since it's larger than 1, it diverges. So E is larger than 1, therefore series diverge. It diverges. We didn't have to use the ratio test to prove it, but we did. We could have just used the Nth Term Test for divergence, and that would have been sufficient. But we went a step further and showed you using the ratio test that it also diverges. Okay. And pretty much that's the ratio test. Okay. Well, I hope you enjoyed the lecture. Hope you learned something. If you have any questions, comments, issues, cares, concerns, worries, or woes, you can always email me, and I'll be happy to answer your email. Or also go back and rewind the lesson and look at it again, and take it a little bit slower, and you might be able to kind of understand what we made an effort to teach and explain. Okay, till we meet again, be safe, social distance, wash your hands, and I'll see you next time.